Later meeting. So, okay, welcome to lecture number 6. Now it is in parallel and distributed computing in the summer term 2025. So today we do a little bit of low-level theory before we go on and do some exercise actually with MPI. So today, first we have the topic loop schedule and tiling, where tiling actually is something that maybe you should do anyway, even in serial programming. I come to what. So it's a little bit related to what we do in parallel programming often, but it's not necessarily completely just for parallel programming. So the main question that we are going to address is how to divide the work between the different workers. So the workers would usually be either our different processes or our different threads. Yeah? And now say we have first of all, we need to know what case we have. So, in many software, actually in a lot of software, different, so usually nowadays software uses different threads and also uses parallel programming in some sense, but most of this is doing different stuff with different threads. Something taking care about the user interface, something taking care about calculations later, please.
It's not an automatic process, like the program has to write the code so it works that way.
Yeah, yes, of course you always have to, the writing the program is telling the computer how to specifying things, how to do it. But nowadays, usually you notice that you can do several things with a program at the same time. Like there's some calculation going on and you still do some modification on the foreground. So if things work that way, you know that there are several threads working, but they are working on different. They are doing different code, right? Because they are having completely different tasks to do. But what we mean in case of so what we usually mean with parallel programming is that we have multiple work items of the same kind. Yeah, so this is the simple, at least this is the simple case, and this is what we often mean to do, but it's not always the case, and we also see one example, mainly in the exercise, where this is not necessarily the case, that every part of the program does the same thing. Yeah. So now multiple work items of the same kind. So this is what we very often have, and of course in sequential programming we do this by a loop. This is processed in a loop. So basically our loop, yeah, looks usually like this. There's a for int, say there's an iterator I that's going from 0 to, you know, the number of work items that you have is n, say, yeah. And then you're increasing this thing, and then you have something to do, and say you call the function do work on I. Yeah. So you have to indicate what work item you are doing. So there needs to be this iterator somehow. So pretty simple. Now what we want to do is we want to split this work somehow up. And the very simple way of doing this is using static, so-called static loop scheduling. So this is the very simple thing that you would come up, that everybody would come up themselves, yeah, if they had to divide work, right? So pretty simple. It means that the subset of the work items is assigned to each process, and now this makes it static without considering the result of the work, or also the expected result of the work. So meaning we have so and so many people, everybody, we have 10 people, yeah, we have 100 things to do, so everybody gets 10 things to do, yeah, and you go off and do your work, yeah.
So no dependency.
Yes, that's the great thing, that you have no dependencies. It's actually you don't even need a master. So maybe you can also think this from a master perspective, yeah? Like there's 10 people coming and one is standing there and gives out the work, but if it's clear, if it's automatically clear that everybody gets to do, you know, their static share, then what you could also do is that everybody comes in the mornings themselves, takes their share, yeah, and start working. So this means they don't need a master that tells them you take this share, right? So they can, because it's static, they can do this themselves. And this means there is no master. There needs to be a program, but there doesn't need to be a master. So because my writing becomes more and more ugly, because each process can determine their own work. So, very simple, say we have a for parallel, Okay, we'll later learn about OpenMP, which we have not yet done. Yeah, so in OpenMP we can actually do this. Yeah, OpenMP. So this is not the correct nomenclature now. Yeah, but it will be very similar. So you do a parallel for OpenMP parallel for. Yeah, and in this you can specify, for example, in j equals to 0, j is smaller than the number of processes. And then you count up j. So now this can be done in parallel. And then inside this, you still have a loop that deals with your particular share. So let's have j. So the number, so you start with j times n divided by the number of processes. And this needs to be an integer, so we'll usually, round this. So if we have, say, 27 work items, say, okay, make it 27, make it 29, so then it's a prime, yeah. So 29 work items, and you have 5 or whatever, 6 people to do the work, then not everybody will get the same amount of work because it cannot be divided that way. So we usually round this, and later int I. Yes, so and then we see whether this is smaller than j plus 1 n divided by num processes. Do I have this? I plus, and then you do your work. Okay, so you have a bigger outer loop and you may have a smaller inner loop. So that very simple way of doing this can be a good idea, or I mean, this is the natural thing how you would come up with it, right? You simply attach the same amount to everybody, or to all the processes, and this is good if the execution time or other resources associated with this of do work of I is the same for all I. So this does not need to be the case, right? So, I can hand out homework, different kind of homework, and you get a very difficult homework, and your colleague gets a very simple homework. Yeah, maybe that's. I mean, hopefully this is not the case. But you see, but you can think about very, very many tasks that can be very different. So, for example, here this building has 17 floors, yeah. So then there would be 70. So there would be twice as of this as number of toilets. So 30 something toilets, yeah. And people get attached to cleaning the different toilets, and one toilet is very dirty, and another toilet hasn't been used for 2 weeks, so it's actually completely clean. So, it's different. They will need different amounts of time because they have different yeah, so the do work is not necessarily the same for all I.
But if you are assigning this, then you are like a master, so to say, who decides
Okay,
what's
now
done.
the assigning, it can be self-assigned. So because the program, okay, so all of them run a program, yeah, and this program, so in MPI we would usually, so what in MPI the way this usually works is the first thing is you start looking up what is your rank, yeah. So who am I, yeah, and from who am I determine what is my share. So if I have a static scheduling, I can easily determine what is my share, yeah, by simply, so if I'm process number 5, so I get the 5th share of work, and then I pick it up myself, and then I do not need any master, yeah. So because we don't, so the program is not the master. A master is another process that that tells, is one process that tells other processes what to do. Yeah, but this is not necessary because you can the process can determine him itself what share it is supposed to do. Okay, now having said this, with this cutting, with this cuts of data, we have to, of processes, of work, we have to also take into account how things are processed with regard to data locality. And data locality is, so for example, sticking with my stupid idea about the toilets. Yeah? So you notice in this building on every floor there are 2 toilets, yeah? One for male and one for female, and nothing for whatever else would be there, yeah? So there are 2 toilets. Now you could split, say there are 4 workers that clean these toilets. Now there are different ways you could split them. So for example, you could say, or let's say there were only 2, right? Now you could have the idea, just for organizational purpose, to say, okay, then one of them does the male toilets and one of them does the female toilets. Yeah? So that has several implications. For example, they are not the same setup, so they are not the same size, so they are not the same amount of work. But more importantly is that they are usually next to each other, yeah, and there is something that is similar to a bus in our computer, yeah, namely the lift. So this would mean that each of the 2 workers would have to go to each of the floors, yeah, to do the cleaning of either the male or the female toilet, right? So then you easily notice that from a locality point of view, this is not a very good way of cutting things. You should rather cut the building in 2 parts, so that that one worker will only process the upper floors and one worker will process the lower floors, right? And this is what we call locality. So once the worker has done the male toilet on that floor, they would proceed to the female toilet on the same floor, so that they don't have to move around and waste time with this. So, and this is also usually the case here in the most of the problems that we are dealing with. So there's distributing work, so distributing the work that is using consecutively stored chunks of data. Thick. So we call this blocking. So we have blocks or tiles. Okay, we come to tiling. I mean, maybe I'm a little bit upset with this inconsistent. I said the naming is inconsistent, or maybe I'm myself not completely aware of what is the right naming. But I observed that there is some. No, not no. How we usually describe this, whether we use the word blocking or tiling, yeah, and what exactly is the difference between them. So maybe I'm talking nonsense here, but let's get my. So the so a tile and a block basically is the same thing. It's a part of a larger domain that you cut out. Basically, you have your data in your RAM, somehow like this, and now you would. So what you often observe, this is not necessarily the case. Not necessarily is this the case, but often it is the case that work that has to be done is connected to data that is in the memory, and usually the work the only difference with the work is that they use different data. Yeah? And data always has a location. This means you can split your data up into say these blocks or also tiles. So I guess you get the point. I'm going to stop here, and you do the work, and you attach the worker I mean, it's not work, it's worker. So you attach the worker to the data. Such that you have this data locality. Yeah, so you don't need to go far away to collect the data you are working with. This is in particular important if you are on a distributed memory machine, yeah, where the data of a different block is actually on a different machine, so that it would be very expensive to access it. So blocking can improve data locality. This can also be useful in the serial case, as we'll discuss in a minute. Yeah, but it's very important if you have a distributed system. So why do we want to do this? We want to use good use of caches, and we want to minimize minimization of inter-process communication. And now this is a little bit related to the kind of problem that we are usually solving, that engineers are often solving. So there's of course different kinds of problems, but one problem that we are always concerned with as engineers is solving partial differential equations. That's if you do fluid dynamics or you do solid mechanics, yeah, all of these things are solving partial differential equations. Then the operations often depend on data in a certain neighborhood. So, partial differential equations are partial because they use different dimensions. Yeah? And in engineering, these very often correspond to some spatial dimensions. They could also be completely abstract things like cost or water supply, and all these things could also be dimensions. Yeah? But very, very often the general case is that we have some spatial layout that we have to deal with. So, and in this case, our data basically is related to our geometry, and say there would be a coordinate x and a coordinate y, and of course in 3 dimensions this only becomes more complicated and severe. So, and now somehow you have to store your data in this. Say, so there would be data points or something like data points, and they are stored sequentially, usually like this. So the point of all of this is that the computer memory is one-dimensional, yeah. Even though we are having a multi-dimensional setup. So, and what your method that solves the partial differential equation usually does is it processes one point in the domain at a time, and this one point it is processing depends on neighboring data. Yeah? So locality, unfortunately, so there are completely local problems that only need the data on one point and does not communicate with the data on the other point, on the neighboring points. These things exist, yeah, but they are very seldom. So usually what we have is that when we process the point here in the center, we depend on the neighbors. And in this case, this looks pretty easy because it depends on its left and its right neighbor. So data locality, so this data will be very local altogether, will usually be very local. Yeah. However, because there's a partial differential equation, so there's not only the x dimension but also the y dimension, it also depends on data that is not in the fast track here. Okay, so then this is further away from this point. And if we now unroll our memory, and say this is somehow, these are some divisions which I now just, okay, I did not count them here as, say our point is this here is our point xy, right? So then this guy depends on its neighbor here. Say this is x minus 1, and it depends on the neighbor there. That's x plus 1. However, it also depends. So this is very close. So when you read a cache line, potentially it will be in the cache line, right? So, but then it also depends on this data that's further away, because it uses multiple dimensions. So, and this is of course our RAM. Okay, now you could say several things about this. Yeah. So there is data here that is close by that you can easily read, and then there's data that's further away that you may not easily read. And usually the ones that is not easily read, so the one in Y, they are producing the bottlenecks. Now, whether this is a problem or not now depends on the size of your system, because as you notice, this y plus 1 and y minus 1, this is not extremely far away. Yeah, it's just on the next line. Yeah, but whether this is far away or not far away depends on how long such a line is. So it could be far away, it could not be far away. Yeah? So in terms of what you have as cache lines or caches, and you remember there are different divisions that you have to look at. The length of a cache line. You have a level 1 cache, level 2 cache, level 3 cache, yeah, and depending on whether it's still in that one or still in the next one, yeah, or not even in level 3 cache, this makes the big difference. So you can improve locality also in this unfavorable direction. So there's very clever ways, but I'm now just using the intermediate clever way, I would say, yeah, by splitting up your domain, in these blocks, in these smaller blocks, and you're storing the data in these smaller blocks. Of course, the question is, what is the block size? Well, you will choose the block size such that this somehow corresponds to your cache sizes. Yeah, so that you could put one of the blocks within the cache that you want to use it for. Yeah, because if you do, now you see, what you did is you made the lines, so the lines in x direction, you made them shorter. Yeah, so the distance between this blue point, this blue data point, and this further away data point, they became smaller. Yeah, and so they can more easily fit in the same domain. So now this is splitting up the blocks, and then there is splitting up the operations. And now this, in order to distinguish it, I'll now call this. I write in black loop tiling. So, okay, so this is called, we can call this block domain decomposition, because we'll cut our domain in parts that are small enough that we can easily handle them. Yeah? So in tiling, in what we call tiling, we do not necessarily split our data in this way, but we split our work in this way. And this is also useful even if we do not do parallel programming. So similar to block-based domain So loop tiling, which we do inside a process, can improve cache performance because you make better use of the cache. So, as an example for this, let's try to do this by an example. And the classical example for this is matrix multiplication. So first, let us remind us how we would do a matrix multiplication. In the first place, we would put this into two. Okay, say there's an n time. Okay, say this is n times n matrix. Yeah, n times n matrix. So how would we multiply an m times n matrix? We would have one loop over I. Then we would have one loop over j. And then we would actually have one loop over k from 0, and this also goes. See, we get matrix. So this is an n cube process. Yeah, it's an expensive process. This is also why we want to accelerate it. Yeah, but I mean, this is so now. I mean, the machine learning things, they all work with this matrix multiplication, and this is why NVIDIA makes so much money now. Because they have their tensor cores that do nothing else than matrix multiplication and doing this very, very fast. Yeah. So the question how you can do this extremely fast is of course of tremendous importance if your business is machine learning. So, I mean, this means we are usually not programming this anymore because we use hardware where this is, implemented in hardware so that it's really, really fast. Yeah. But suppose we do this in software. What we do is we accumulate in a matrix. So we want to multiply matrix A times B and get out a matrix C. Yeah, so this Cij, so these are the indices. These are, of course, we start with initializing C with 0. I'm not writing this here. And then we accumulate these things here, A and K times B, K, J. So, and then we close all of our brackets. Okay, so you're familiar how we multiply a matrix. This should not be a big issue. So, and this is the trivial way of doing this. So how can we improve this?
Every loop to a different process.
Yes. So this is no, not every. Okay, no, not. I mean, the loops are inside each other, so you cannot put the different loops to it. So what you can always do is you can distribute the outer loop. I mean, if you want to parallelize things, that you would distribute the outer loop.
Because you don't need to do all of the same. So when you're doing matrix multiplication, you can do each.
Yeah, you do each row with each column.
As it's independent from each other, you can do the same thing, I guess.
Yeah, there's independent work that you can do. But suppose now, okay, now there are different aspects to this. So first of all, the outer loop, you can of course split them up and do part of the work on different processes. Yeah? But suppose you have a very big matrix, so that even each process still has a lot to do. Yeah? So you would usually try to optimize this thing on several layers and levels. Yeah, like you distribute it over several computers, then you make it, then you make it cache fast, and then when you have done also this, you may also use AVX to vectorize it. Yeah, to make it even faster. Yeah, in reality we use all of the above, right? But now we have to understand the different parts of this, and loop tiling now is not the domain decomposition part where we distribute it on different machines, but suppose we are now already on one machine and we want to accelerate this on the part that is assigned to one machine with one machine, within the machine. So now with tiling, this works like this. We have to decide on tile size. So this is how we split up our problem, and the tile size is something that is specific, that would be specific to your machine and is related to the different, whatever cache line, cache size, or vector size, yeah, that you can handle. So that would be pretty machine specific. And then, do I have enough space? Yes, I do have enough space. So then, what you're going to do is you simply split up these loops again. So you'll have more loops. So we'll have the outer loop int I01. So we do this again from 0 to n, but instead of now increasing I by 1, what we do is we increasing I by the tile size. So we don't proceed in steps of 1 each, but we process in steps of the size of our tile. The same thing we do now in Y, and now the assumption that I make here is that the tile size in X and Y are the same, but this is not absolutely necessarily the case. But you see, I don't want to make it too complicated. J plus, so this again is the tile size. And we also split the K loop in the same way. K is smaller than N. K plus equal to tile size. Oops, I can't draw these brackets. Okay, so these are all the loops. Now all the outer loops where we go in big steps. Yeah. So from tile to tile, say, and now we have to loop within our tile. This is, we have to have these loops, all of these loops again. So we'll have, say, I is equal to I. Now this is a semicolon. Doesn't go well with two i's in front. I is smaller than I plus tile size. So this is iterating within the tile. And here we go in steps of size 1, of course. And then we'll have so we do the same thing for the J direction. So see, J is smaller than J plus tile size and J plus plus. And also we have to do this in K, but there's a small optimization which I also include here, that we use a local accumulator. Okay, I'm explaining this in a minute. So we do now for int k, kk is equal to k, and kk is smaller than k plus tile size kk plus plus. Now comes the loop. We do the sum is the accumulation of AII KK times B KK JJ. So, and I hope I didn't make any mistakes. So now we put this into the local sum, yeah, because you know, the outcome, so if you remember this, let me go back here. So this Cij, so this does not depend on K, right? So I could have already wrote down this in a more efficient way here. So the thing with this example that we have here is that if we address the matrix Cij, yeah, so then every time we would have to write into this part of the matrix, and this may be further away, or I mean, this is because it's a matrix, it's potentially in the main memory. Yeah, it could be taken into a cache, then it may be okay. Yeah, but the idea is we would always write something back to main memory and always to the same position. So what we could do instead is accumulate this in a register actually, and once we are done with calculating this, we can put it back to the main memory. So this is why we'll put the sum outside, and once we have done this, we put this simply here. Okay. And then we close all of our brackets, which I believe are 4. So now, is it clear what we have done? So basically, we have this big loops, yeah, that go through the entire matrix, and instead of going from one end to the other end, yeah, we take some things that we call tiles, which are now not distributed in memory, but distributed in the processing, where we stay local within one part of the matrix, yeah, do our calculations, our partial calculations there, so that this tile has to be chosen in such a way that it fits into that part of our cache that we care about. Which part of the cache that we care about depends a lot on how big our matrix is, right? So we do this calculation locally, such that within this AII, yeah, we are reading the same data again and again before we go to the next tile, where we again read the same data again and again. Yeah. So this is similar to domain decomposition, but it is kind of a domain decomposition only for the cache. So we still have the entire domain in our main memory, but and we still process these things sequentially, yeah, but we cut out a part of our domain that is attached to this particular process and operate on this as intensively as possible, and then go to another part of the domain, load this part of the domain, and go on. So this is what we mean by tiling, yeah, and it's very similar to domain decomposition.
One question. So there's a lot of nested loops here. So one would think this is like less efficient than the other one. So it's more work to do this cache optimization than just having the simple three nested loop, I guess.
So it's more work for the programmer, obviously. Yeah, and also whether this helps you or not depends on how well your tile size fits to your machine. Yeah, but so the important thing here is that you reuse the data as often as possible before you go to new data.
Because you're always staying in the same cache.
Yes, you're always staying in the same part of the submatrix. Yeah, so what you basically do, you do submatrix multiplication, and then after doing the submatrix multiplication, you add up the different parts. Yeah, so this is what then happens down here. And this is more efficient because it has less cache misses than if you do the entire matrix. The thing is, it is maybe not so easy to see this in a basic example that we would now do so for example, if you do this in your homework, because this problem is small enough that it fits in the cache anyway. So because if you take your tile size, the same size as your entire matrix, then it will become the naive way. But the point simply is that in practice we often deal with very, very large matrices. So, with all these things, it is always like this, that at least the outermost loop, in general can be run in parallel. But load balancing, so how the work is distributed, this load balancing, can be poor if the work items depend unpredictable on the iterator I. So this is obviously in matrix multiplication, this is not the case. Yeah. So in matrix multiplication, we know exactly how much work we have to do in each point. Yeah. So, but in there are cases. So, for example, one interesting case is when you compute the number of primes within a certain interval. Then, for example, if you think about how primes are computed, then the work that you have to do depends a lot on what interval you have. So, I mean, computing the primes in the interval from 1 to 100 is much easier than to compute the number of primes in the interval from 1000 to 1100, even though it's the same numbers, the same amount of numbers. Yeah, but since you have to check against many more, in the case of the larger numbers, there will be a big difference here on work that you have to do with regard to where you are in your domain of computation. So this leads us to the second part, namely the dynamic loop self-scheduling. So this means work is not always the same. So you have to dynamically determine what to do. So, and now the easiest way you could think about this is that workers come, take some work up, do this work until they are done with their work, and then when they are done with their work, they go back to where work is distributed. So see, there must be a place where work is distributed, yeah, or pool of work, and get new work to do. So now why is this dynamic? If somebody has very difficult work to do, so this person or this process would still be occupied, yeah, while others that have easy work to do just come back and get new work. Yeah? So this is called self-scheduling. So if there is a worker that is idle, so idle workers just request work from a master process. Now what we need is a master process. This is a process that takes care of what work has already been given out. And this leads to the need for bookkeeping. So the master process has to do the bookkeeping on what work, of the work that is being assigned, or at least the work that has not yet been assigned. So master processes, we computer scientists are kind of always some liberal thing, I believe. So they don't like slavery. Yeah. So master-slave processes, they don't like this. The masters are bad things in parallel programming, and yeah, not only for political reasons, but also because masters are slowing things down. We like if everybody takes their own work out.
Question.
Please.
The difference between the other case and this case is before the processes just take the next task, and here they ask the master for.
Okay, so the next No, this is the same. No, there are only so far we discussed only two, namely that everybody gets. You come there in the morning. You know that there are altogether 5 workers. Yeah. So you come there. You take a fixed share of a fifth of what has to be done today, so you do this, you're done, you go home, no matter whether your colleague is still working or not, because in the morning, everything has been taken up by somebody, yeah, and it's not redistributed. Now, obviously, what we do here is that we do not distribute the entire work immediately, but you basically come there and you take up one work item, and then when you are done with your work item, you want to pick up a new work item. But now you have a problem, because previously, in the first example, you simply knew because it was all static, so you can easily calculate who is taking what. Yeah? But now, since we do it dynamically, you have to determine whether something has already been done or has not been done, or whether some work item has been picked up by somebody or not. Previously, you did not need to care because you had your fixed share. Yeah? Now it depends on the others. So then there needs to be somebody that keeps the book on that. And this is the master process. The master process keeps the book. So let us try to understand this. So what we do a lot in when we try to optimize our work is we do performance modeling. And for this we'll have to write some equations. So we determine that n is the number of work items to be distributed. P is the number of processes. B is the average execution time of a work item. So average means we are not, what we are doing now is not necessarily very accurate. And now it has sigma. Sigma of P is the dispatch time. That now comes of a work item. So this kind of self-scheduling, so dispatch time is you get up from your desk, you go to the place, give me some work, yeah? And take this work back to your desk. So the self-scheduling requires that the work has to be big enough, if you will. So this is useful if the execution time of the work is much bigger than the detachment time. I mean, this hopefully makes a lot of sense, but sometimes, you know, I mean, like you could, it's the question whether you order something on Amazon that would take you 10 minutes to make yourself, right? Then it's better to make it yourself, yeah? So because this, the dispatch time is the time that you need to get to actually pick up the work. So why is this a problem? This is a problem because the bookkeeping is something serial. So this may, okay, so the thing, in reality we use a lot of master processes, and in reality it very often doesn't make a very big difference Yeah, so the master process doesn't take up a lot of time because we usually have only few workers. But in the theory of parallel programming, we are always thinking about what happens if we have millions of workers. And nowadays, this becomes a pressing issue because because nowadays we are using these NVIDIA graphic cards, yeah, that have hundreds of thousands of processors. And now it becomes really a question, what happens if we distribute the work in a very, very finely granular way. So, there we don't want to have serial execution. Okay, now we have to do a little bit of modeling, which may or may not be of concern, but say the dispatch time is expected to grow asymptotically with the number of parallel requests. Okay, now see, you need to have, let me draw this picture here. We have the number of processes, yeah? Then we have that grows in this direction, and we have the dispatch time here. So then it makes absolutely sense that there is a range where you have a constant dispatch time, right? So you go to a place and okay, so say you go to the supermarket and buy something. This is this or yeah, here to the yeah, okay, supermarket, you buy something, right? So if the counter is empty, yeah, so you pick something up and then it just takes the time that you have to pay. That's the bottom line. Yeah, so no, as long as there are few people in the supermarket, so few people that the counter is always empty when you arrive, then taking up something from the supermarket has a constant time. Yeah? So, but this is as long as there are few people in the supermarket and they do not constrict each other. Once a line is forming, yeah, then the time that is needed to get something from the supermarket will then increase linearly with the number of people that accumulate in the line. So after some time, so this is what we call pre-asymptotic. And this is asymptotic. So this may not be a kink. I mean, this may go a little bit more slowly, yeah. But up here we'll have something that is related to that is proportional to the number of requests that arrive, yeah, because they constrict each other, times another constant that we call now sigma infinity. So, and the limit for p going to infinity. So now the work that each worker has to do. Say we have a number of, we have a constant, this is strong scaling, yeah, constant amount of work in. So we have to do n divided by p is the amount of work that you have to do, but n divided by p is how often you have to dispatch something, basically, but you have to dispatch this with p, and this, because n of p asymptotically is proportional to p, will become n sigma infinity. So now this is strong scaling. Meaning strong scaling is when the amount of work does not scale up with the amount of workers. Strong scaling, speed up, is limited by the master. Process, the serial execution. Okay, again, I have to say that this is not necessarily of importance for you, because this is an asymptotic thing. Yeah? And if you have a relatively small system, like you distribute your work over 32 processors, this is not yet asymptotic. As long as your master can easily handle this, you will always be in a pre-asymptotic case, and you may not even notice that there is such a problem. Yeah? But asymptotically there would be such a problem. So then our speed up is always the time that the serial code would work over what the parallel work would work. And if we are in the asymptotic, I mean, this is a big if we are in the asymptotic way, then we have, for the serial work to do is n times, so the amount of work times the time that the work on average takes. This we have here too, just that the amount of work is divided by the processor, by the number of processors, plus the amount of work, so what we just computed here, the amount of work times the dispatch time, which we can rewrite, because there's an n everywhere, we can write this P into phi sigma plus b. And now if we take the limit of p going to infinity on our speed up, we see that this becomes b divided by the dispatch time. Yeah, so the maximal speed up is the average time that you work for one item divided by the dispatch time. Yeah, so this is the maximal thing that you can reach. So this can be improved by what we call chunk scheduling. So this is, we do not dispatch one work item at a time, but we dispatch several work items at a time. Yeah, so you go to the so there's the difference. You go to the supermarket, you buy one item. You go to the supermarket, you buy many items at a time, right? That may be more useful. So, the overhead of self scheduling can be reduced by assigning chunk of work items. So what you have to start up with is you have to determine a chunk size. So chunk size K, so this is how many work items you put together in one chunk. Then we have to redo our modeling here a little bit. And I have to remind you, this is modeling. So in models, there are assumptions. Whether this is true or not depends on whether your assumptions make sense. Yeah? So this can be like this, and it can be in a little bit different way. But say this is again the dispatch time over the number of processes. There will again be a constant, and then after some time there will be an increase. But now this increase is because you ask less often to get more work from the master. The master is lesser occupied, yeah, and has less work to do. So then this becomes P divided by K, yeah, because 1 divided so it has K times less work to distribute than before. So this is why it would look like this, and then this TP would be N divided by K and P. So this is how many times something is distributed, but the work that has to be done is then K times B. So you get less amount, you get fewer chunks of work, but the chunk of work is proportionally larger. Yeah, obviously. So this is now because it came plus the number of assignments that you get is again theta and sigma. Did I say theta before all the time? I don't know. So this is very typical for me that I'm mixing these things up. I mean, so it's sigma, yeah. So let's have this again, this N divided by Pk sigma Pk. So because there is in this becomes Pk 1 over P, so P over K in sigma infinity, this will become N sigma infinity divided by K square, at least in the asymptotic range. I mean, spoiler, of course, here is this doesn't work very well if you are in the asymptotic range. So you would like to dimension it in such that you keep outside the. But this is something that's supposed to help you to stay outside, because we now have this TP N K P KB plus P K sigma infinity is also N divided by P B plus P sigma infinity by K square, and this serial execution time is still N times B. So the speed up in strong scaling is then Ts divided by Tp, which is Nb n divided by Pb P sigma by k square, which you can also rewrite as k square Pb divided by k square b plus p sigma infinity. And now if you take the limit of p going to infinity, what you actually end up is that in the asymptotic limit, the speed up grows with k square. Actually, this is a little bit surprising, and potentially it is it's not necessarily very important in practice, because in practice you may not be completely in this absolutely in this range, yeah. But because you had this problem before, in that if we split up, simply when the problem is that, of course, it makes no sense to take infinitely many processors, right? So this is now very much simplified, such that it does not necessarily make that you practically see this k square case, yeah. But you would at least see that even if you replace this thing here with sigma 0, yeah, what you would end up in this non-asymptotic case then would be kb by sigma 0, which would still increase linearly. So anyway, you get a much better speed up depending on your model that you apply with using this chunk size. Okay, I have one maybe a little bit more practical approach, how in the end today this is guided self-scheduling. So now this is a relatively primitive method, GSS, guided self-scheduling. Okay, just an example of what algorithms have been thought up. So we attach chunks, but the chunk size does not need to be the chunk size k, that does not need to be constant. And the basic idea here is that a process that starts later gets a smaller chunk size. So the way this is exactly done is, okay, may depend, but here's an idea how it can be done, but I'm pretty sure that this is not always the optimal way of doing it. So again, you have the number of work items, you have the number of processes, and you have R. R is the work that is still left to do, the work items not assigned yet. So we start at start, this is of course N. And then there would usually be a minimal chunk size that would be at least one work item, but can be larger. So this algorithm works like this, that the next idle worker gets the ceiling of, I mean, it must be an integer, yeah, of work items. There we use the ceiling. The amount of work that is still there divided by the number of processes. Only if, and this of course, if this is larger than the minimal amount of work incoming else. So we have to do this. This is important because otherwise, if we don't stop here, yeah, this R by T. So for example, there's only one work item left, but we have 5 processors. Then they would always argue who is doing that work because it is smaller than this here. Yeah, so this is why we need to have this came in here. So then, as a very last thing, let's do this example. Say we have a 100 things to do, and we have 5 processes, and we say that our car min is equal to 1. So then R will start with 100. And here we have our process, and now the process number 1 gets an assignment or number of assigned items. So this will 100 divided by 5, this will get 20 items. Yeah? So it's the first one that comes to work gets the most work because they can also already start while the others are standing in line to pick up their work. Right? So then the next one, so then 80 are left. Then comes process 2, and this process gets then 60 assignments. So now it's debatable whether this is a fair distribution. Maybe not, yeah, but this is, I mean.
But just assuming that there is this time between the first and the second request for work.
Yeah, so when they start, okay, so you see, this is of course assuming that this may not be perfect, this method, yeah, because maybe it's not perfect because we have very few work items here, yeah. So if we have many more work items, then this may not. Okay, so I mean it's a question when everybody comes to work in the morning, yeah, and so that you start to distribute it like this looks a little bit unfair. But I mean, so I would suggest that because taking up this work did not take so long, that the second worker is so that the first worker will probably not come back today. So you know, he's maybe the one that does the most, maybe, yeah. But the thing is, the assumption is that this doesn't matter that much, because when you are done with your work, you pick up new work. And the idea here, of course, is that you do not know beforehand how much time you need for your work. So if these 20 work items all take the same time, then then static work distribution would be better. Yeah.
Kind of pessimistic maybe, because you always expect that the next people coming is going to take very long. So you just give all the possible work to the first one and just wait till the second comes. Because if you give less work to the first one, okay.
Yeah, it's okay. Maybe I believe this is not the optimal way of distributing work. Yeah, but it's a relatively simple way. Yeah. So now what we left up with is 64. This goes to worker 3, and then then this worker 3 gets 13 assignments. Then okay, now I assume that I just did this correctly. We come to worker 4. It gets 11 assignments. Then we'll left with 40, and our number, so he gets only 8. You see, much less than the first one. But then it depends. So maybe he is also the first one to come back, because simply the next one that is done with their work, right, coming back, this would have 33 left, and that gets 7. Then there is 25 left, and the next one gets 5. Then there's 20 left. Next gets 4. Then there's 16 left. Then next gets 4 again. Then there are 12 left. Then the next gets 3. Then there are 9 left. Next gets 2. We have 7 left. Then the next gets 2 again. And then we have 5 left, and then next gets 1. And because this is the minimum, we simply distribute the minimal workload to everybody. Okay, so this now anyway taken some overtime. This is now the lecture. We'll make a small break before we come to the exercise. Let me. Okay, I got stuck with my computer.